at chemical kinetics. Now, our subtopic could be reaction rates or rates of reactions. Now, in thermochemistry, we've learned that energy involves chemical reaction. And then there are reactions that involve heat, which we call exothermic reactions, and reactions that absorb heat, which we call endothermic reaction. In order for any chemical reaction to be feasible, it must occur at a reasonable rate. So we have to look at how reaction rates occur. So in this lesson, we'll be looking at the definition or explanation for reaction rates. We'll also look at how to identify the factors that affect the rate of chemical reactions. Then we'll also deduce rate law equations from a reaction which is said to be the RDS reaction. The RDS stands for rate determining step. We'll look at what it fully means in our next slides. Then we'll also deduce rate law equations from an experimental data. So here we'll be given a table of values, concentration of 2 or more reactants, and then maybe a rate constant, and then we'll ask us to deduce a rate law equation from that data. Then we'll finally look at how to deduce rate law equations when you are given concentration and time. Good. So, first question we ask ourselves is, what is reaction rate? To the layman, the rate of reaction will simply refer to how fast a reaction goes. So, on the bottom of your screen, you can see 2 pictures there. We have a chemical reaction going on. There are 2 chemical reactions. The first one occurs in iron, and as you might already know or observe, the rate at which iron rusts is very, very slow compared to the rate at which wood burns. So burning is very fast compared to rusting. So this should give you a fair idea of rates. But as chemists, we are also interested in the quantitative approach, how to calculate rates of reactions. So we define rates in terms of formulas. So the first definition there says reaction rates or rates of reaction is the change in concentration of a reactant or product with time. So the rate at which a reactant is able to be converted to a product. So for instance, in the kitchen, we can consider your kitchen as a lab. You are preparing banku. The rate at which you are able to convert the cassava dough, corn dough mixed with water and salt to your banku will be the rate of reaction. And it depends on several factors. The heat being applied, the concentration of the cassava and corn dough's mixture, and a whole lot. So I have a simple equation, a simple equation there, reaction or reactants moving to product. So for instance, if I have reactant A being converted to reactant B, how do I determine the average rate? So here, the average rates can be calculated by finding the change in the number of moles of B, that is the product, over the change in the number of moles of A, that is the reactant. Sorry, let's go back. Now, average rates can also be defined in terms of concentration. So the symbol there, the square brackets there, represents concentration. So you can also calculate the average rate when you are given a simple equation like this by finding the concentration of the product per unit time, or the change in time there. So this is a little bit of differential equation. Those who have done calculus will understand this better. We'll look into that. Now, the average rate is positive here because a product is being formed. There is an increase in the concentration, or the number of moles in a given solution for the B. And the average rate for the second one, that is A, the reactant, will be negative because a reactant is consumed. There will be a reduction in the reactant. Okay, so yeah, let's move to the next slide. So before we can understand perfectly reaction rates, we have to look at 3 theories that have been established, and we call it the theory of reaction rates. So I've summarized it into 3 because they are the most important points there. Now, the theories are such that we normally deal with particles. We remember from our elementary chemistry or physics that all matter consists of particles. So we're going to deal more with particles. So particles are in a constant rapid motion, and this results in many collisions. So if you have a cylinder filled with gas, the gas particles are always in constant motion. Yes. If you have maybe wood in fire, whilst you are burning the wood, there will be constant motion of the various particles in the wood. Even though if you put iron in fire, there is constant motion of the particles. So in this world, there is nothing like no motion. Everyone is moving. Even you, the human being, sitting at one place thinking you are not moving, in actual sense you are moving because there are particles in your body moving here and there. So this theory even applies to everything in nature. Yes, so only a small fraction of the collisions lead to chemical reactions, and these are called effective collisions. So it means that before a chemical reaction can occur, you should have effective collisions. If there are effective collisions, then a chemical reaction will be able to occur. If not, then a chemical reaction will not occur. You can also picture the Banku scenario. Until the point where let's say that there is a good collision between the condo molecules and then the cassava dough molecules and water and everything. That is when we form our Banku. So it means that we have effective collisions. But let's assume your fire is very, very, very low. You are using low heat or low temperature. What will happen? It will take a very long time for you to achieve the effective collisions. You might not be able to even achieve that. Therefore, a chemical reaction will not occur. Then, this one, the third point, deals more about the graphical representation. We'll talk about it we'll have at least 2 or more graphs to explain. It says that colliding molecules or reactants need a minimum amount of energy before a reaction can occur. This minimum amount of energy is called the activation energy, and the symbol there is EA, E subscript A. That is the symbol for activation energy. Okay, now let's look at the factors that affect or influence the rate of reaction. We have several factors. We have concentration of the reactant. We have process by which the reaction takes place. Then the temperature, presence of catalyst, and then the reaction mechanism. We also have pressure. Yes, so they will be looking at I think about 5 or so of those factors. So they're your syllabus. So we'll take the first factor there, which is temperature. As you can guess, if you can guess correctly, whenever we increase temperature, the rate of reaction increases. You observe this in nature all the time. When there is a lot of heat, the reactions tend to happen very, very, very fast. So back to your cooking scenario, when there is a lot of heat or there is high temperature, you're able to finish cooking fast. Yes, you might even burn the food. Yes, means the rate of reaction is very fast then. So increase in temperature increases the rate of reaction because the kinetic energy of the molecules increases. Hence, the number of effective collisions per unit time is increased. So we are looking at the fact that every substance contains molecules or particles, and these particles, according to kinetic theory, energy theory, are always in random motion. Now, if we want a reaction to occur, then we need to increase the temperature. Once we've increased the temperature, the particles will gain enough energy to move, and that's what we call the kinetic energy. And this will also increase our probability of getting effective collisions per unit time. So that will also make the rates of reaction increase. Now on my graph here, I have two graphs drawn. So the first graph there with the red ink is a reaction rate or a reaction which has a higher temperature. Then the blue represents a reaction with a lower temperature. Now from the origin or from the x-axis to the peak gives your activation energy. So for a reaction to occur, we have to make sure that our molecules, our reactant molecules, are able to get to the activation energy or surpass the activation energy. So when you increase the temperature, it lowers the activation energy, making the molecules able to reach there, and then therefore increasing the rate of reaction. So that is that. Let's come to how it affects about temperature, the number of moles or number of particles in a given volume of solution. So the rate of reaction increases if the concentration of reactants increases. If the concentration of reactants increases. And I'm explaining here with a very simple scenario. I believe most of you have come across hydrogen peroxide. It's one compound that you can get from your local drugstore. And the one we have there in the drugstore is diluted. Normally we use it to dress sores. Some people use it for teeth whitening and other home activities. So we consider the decomposition of hydrogen peroxide. Naturally, when it is pure, it's in a liquid form, and when you just put it in a bottle or something, it tends to decompose. Yes, and it will even explode into a gas that is water vapor, and then oxygen will also be released. So when you have hydrogen peroxide in its pure concentrated form, the decomposition is fast and explosive. So this is a reaction. Decomposition is a type of reaction, and it's going to be fast and explosive because you have in its pure concentrated form. But when dilute, such as the drugstore peroxide, the reaction is slower and the solution is stable for months. Yes, so the solution doesn't tend to change to vapor. Yes, it stays for a long time because now we've been able to dilute it. The rate of reaction decreases. Good. I hope you're understanding so far. Any questions so far? Unmute your microphones if you have a question. Should I continue? Any questions so far? Any question? Not getting responses. Oh, their microphones are out. Okay. Okay. So I can continue then. Now, this is a picture showing what happens when we add concentrated sulfuric acid. We can get this from our car batteries, our normal car batteries. That you shouldn't do this at home. Don't try this at home, except you have the necessary safety gadgets, goggles, hand gloves, and the aprons to put on, because concentrated sulfuric acid is very corrosive and dangerous. So here I have two beakers here. In beaker 1, the first beaker, I have sucrose. And sucrose simply refers to table sugar, the normal sugar we use for cocoa or porridge, tea, or breakfast. So that is sucrose. And here the chemist is adding concentrated sulfuric acid. But to this, he's adding dilute sulfuric acid. So with the concentrated sulfuric acid, because the concentration is high, you can see after 15 seconds how the rate of reaction has gone so fast. Yes, so you can see the product being formed here. Whilst in the dilute solution, nothing seems to be happening. There is a reaction going on, but it's taking a very long time. So here, the rate of reaction is slow. So it means that concentration depends directly, or the rate of reaction depends directly on concentration. Yes, concentration and rate of reactions are directly proportional. So after 60 seconds, you can see what has happened here. So this explains that increasing the concentration of reactants also increases the rate of reaction. So that's right. Catalyst also affects the rate of reaction. Addition of a suitable catalyst increases the rate of all reactions. The catalyst provides a new reacting pathway with a lowered activation energy. More reactant molecules will now have their kinetic energy to be greater than the activation energy. Hence, the number of effective collisions will increase, and hence the rate of reaction will also increase. Our collision theory realize that when the effective collisions are increased, the rate of reactions is also increased. We move to the next. We see a graph there. So this is what we are talking about. So the first graph in green, first curve in green there, is an uncatalyzed reaction. That is a reaction without a catalyst. And you can see it has a high activation energy. The peak there is called activated complex. So here we need a high activation energy to enable the reaction to be complete. Okay, so see what I'm getting this is. Okay, but looking at this one With a catalyzed reaction, we have the activation energy lowered. You can see if you compare the heights, this is lower than this. That is the blue graph. So this picture explains what we've been talking about, how catalysts affect the rates of reaction. Good. Now, we are now going to talk about the nature of reactants. The greater the surface area of reactants, the greater the number of collisions and effective collisions, and then the higher the rate of reaction. So those of us who cook, when you use granulated salt, that is the salt in the rock salt, compared to the powdered salt, you realize that the powdered salt makes your cooking faster. The rate of cooking or the rate of reaction becomes faster because here you have increased the surface area of your reactant. Yes. So the surface area depends basically on the nature of the reactant, as I explained, whether it's granules or powdered form. So a powdered reactant will be more feasible or will increase the rate of reaction compared to an unpowdered reactant. Okay. It also talks about whether the reactants are solids, liquids, or gases. This is a simple chart showing the rates at which reactants increase. It takes a long time in solids, and the fastest should be gases. Good. Now let's move to the next slide. Pressure. Pressure only affects reactions involving gases. So when you are talking about gases, then you can talk about pressure. Increasing the pressure increases the rate of reaction. This is because the frequency of collisions, hence the frequency of effective collisions per unit time increases. So in a vessel, if there is enough pressure in a vessel, the rate of reaction will increase. The rate of reaction will increase. Okay. Now, let's talk about how to deduce rate law equations from an RDS reaction. That is a reaction which is considered as the rate determining step. A reaction which is considered as the rate determining step. So basically, a reaction that is considered as the rate determining step is a reaction that takes the the fastest possible time to occur. Let's go to this slide so that I can explain with the notes. Yeah. Okay, so the rate determining step is the slowest step of a chemical reaction that determines the speed rate at which the overall reaction proceeds. Yes, that is the rate determining step, the slowest step in the reaction. So to explain, when you, for instance, you're looking at application in real life. Let's say you want to build a toy car and you need 3 steps to do this. The first step is you have to purchase the parts of the toy. Then the second step, you have to transport the parts home. Then the third step, you have to assemble the toy. In this example, how fast the toy will be assembled will be determined by which of the 4 steps takes the longest time to complete, because that will determine how fast the whole reaction will go. Yeah, will go. So it means the RDS, or the rate determining step, is the slowest of the reactions, the slowest step of a chemical reaction. Okay, so let's go back to our slide, deducing. Okay, so in this equation we have that in a certain reaction the RDS is A plus 2B going to C plus D. Write an expression for the reaction rate equation. Deduce what will be the effect of the reaction by doubling the concentration of A and then doubling the concentration of B. Let's go to so this is our equation, and once it's the rate determining step, in order to get the expression for the rate equation, the general formula for getting the rate equation is R equals K, concentration of A to the power X and concentration of B to the power Y. As I've explained here, the concentration, the square brackets there stand for concentration of the reactants. Okay, so when you read the question and then you've been told that the reaction is RDS, then the stoichiometric number of moles of the reactant is also their respective orders. That is in the equation. If we should go back to our slide. Yes, so we have the number of moles of A being 1. The number of moles of A being 1, and then the number of moles of B being 2. So if you go to the overall reaction, that is the formula, the rate equation, we have A to the power 1, which you don't write, and then concentration of B to the power 2, because when you look at the chemical equation, the 2 there stands for 2 moles. So that stoichiometric mole, the stoichiometric mole becomes the power or exponent, referred to as the order of the reactant. Okay. So we come to the second part of the question, which says that what will be the effect on the reaction when we double the concentration of A. So we have the concentration of A being doubled, but there are some hints here for us to understand. We use these hints when we want to solve rate equations using the method of intuition or reasoning. So for a first order reactant, increasing the concentration of the reactant by n times increases the reaction rate by n times. So if it's the reaction is or the reactant is a first order reactant and you double the concentration by 2 times that, okay, you double the concentration, it means that the reaction rate will also be doubled. And if you multiply it by 3, the reaction rate will also be multiplied by 3. That's the meaning of the first law there. Okay, so then the second one, for a second order reaction, increasing its concentration by n times increases the rate by n squared times. So if the formula, okay, I can see it. Okay, so Michael Fosu, the topic for today's lesson is rates of reaction. Then, okay, some of the students asked me, I asked them to ask you, so try and give me, okay, so Michael Fosu, rates of reactions is our topic. Okay, good. think I have to. Okay, so let's continue. Okay, so let's look at the second point there. So if we look at an equation, let's say an equation, and then the concentration of a reactant has, let's say, 2 attached to it, and then that equation is an RDS equation. It means that that equation is a second order reaction. Therefore, if we triple the concentration, that is, we multiply the concentration of that reactant by 3, it means that the rate should be 3 squared. That will give us 9 times the initial rate. Then for a third order reaction, the rate will increase by n to the power 3 times. So for example, if you realize that your reactant is a third order, that it has 3 in front of the number of moles, and it's an RDS step, then if there are 2, if you are going to increase the concentration by 2, then the rate to be increased by 2 to the power 3, that will be 8 times the initial or the original rate. I hope we are following so far. Any questions so far? Any questions so far? You can send a message or you can unmute your microphone. Okay, so Aposwe says no question. Good. So let's move to the next slide. So going back to our question, this is the equation we've been given, and we are asked to find the rates of reaction. We could get a formula, and we got that. And then, we got the rate of reaction, or the rate equation, and we are supposed to now deduce what will be the effect of the concentration of A. So if you look at A has 1 mole here, so it means that A is a first order reaction. So doubling the concentration of A should do what? Any idea? Please unmute your microphones and let's try to answer this. What will happen when we double the concentration of A?
The rate will also be doubled.
The rate will be doubled. Why?
Because the first order reaction.
Okay. Because it's a first order reaction. Very good. Yes, any other answer? Okay. So I think we all agree with what Charles said, or is that not Charles? Yes. So the rate of reaction will double because this is a first order reaction. Okay. Now, what about the second scenario? We are doubling the concentration of B. what will happen? Another person apart from Charles should answer. Unmute your microphones if you are ready to answer. If not, mute. Yes. Who answered the second part? Hello? Okay, let me look for some of you. Yes, Amayebua.
Sir, the rate will increase by 4
The rate will increase by 4. Why?
because the second order reaction.
Okay, very good. How do you know it's a second order reaction?
Sir, because of the number of moles.
Very good. It's here. And then this reaction or this equation is the rate determining step. It will always not be the case, but because it's an RDS reaction, that's why we are deducing those concentrations from the stoichiometric moles there in the equation. Very good. I think you are all following. That's good. That's fine. So let's move to the next one. So as Amayebua said, the order of the reaction with respect to B is 2, hence the doubling the concentration of B quadruples the reaction. That is, it multiplies the rate by 4. Very good. So let's move to the next part of our lesson, that is how to determine the Rate's law equations from experimental data. So here we have an equation here, and we are not considering this as an RDS equation. This is not an RDS equation, so we check out. Okay, Stephanie, you can't see. Let me try and then do something here. Now how to use this. Okay. Stephanie, can you see now? Is it clear now? Okay, good. So now let's continue. We have a table here. So with this scenario, we are performing 3 experiments. You know, in science, we won't just settle on one experiment. We have to do several experiments before we can conclude our answer. So we have 3 various experiments here, and you can see we are talking about the concentration of the reactants here, and then the rates at which the products are being formed. Okay, so with the first experiment, the concentration of the reactant is 0.25 mole per dm cube. With the second product, the second reactant we are using 0.25. Now, the unit here, molar, you all know it's also mole per dm cube. So it means the rates will be mole per dm cube per second. That's the unit for rates, mole per dm cube per second. We're looking at the derivation of the units later. So I've shortened the mole per dm cube to molar, big M. Okay, so this is our first experiment, and this is the rate of reaction. Our second experiment, we have 0.25 molar for the NO, and then 0.50 for the CO2. The rate is this. And then in our third experiment, we have 0.50 for NO and then CO2 respectively. Okay, the reaction occurs at 50 degrees Celsius. So let's look at the questions. We have to deduce the rate equation, and determine the overall order of the reaction. Then we have to find the rate constant for the reaction at 50 degrees Celsius. So we have two methods of doing this. The first method, which we are looking at on your screen now, is to use the analytical approach, that is calculating to deduce the rate equation. So we are representing the order for the various reactants as X and Y. So this will imply that our general rate equation is R equals K, concentration of A, concentration of B. So here our A is NO, and then our B is Cl2. So if we go back to the table, we are doing experiment 2 over experiment 1. Experiment 2 over experiment 1. The reason why we are doing that is that if you look at experiment 2, we have 0.25 and then 0.25 there. So if you look at the table, we can see clearly that these two can cancel out. So that's why we picked experiment 2 divided by experiment 1, so that we can be able to solve for the Y. So it's an elimination tactics we are using here. Elimination tactics. I think I saw a message somewhere. Okay, someone is asking for the name of the formula, the formula NO. Yes, this is basic chemistry. This is nitrogen oxide. The IUPAC name should be yes. Any idea on the IUPAC name? This is a question to the class. Okay. Okay, that is nitric oxide. Nitric oxide. So that is who is me? Me number 1. Okay, me number 1. That is nitric oxide. Or nitrogen monoxide. Okay, so nitrogen monoxide or nitric oxide. Good. So our approach here is to eliminate the X so that we can comfortably solve the Y. So that's why we divided experiment 2 by experiment 1. So this will be equal to that over that. On your calculators, if you punch that, all of this will give you 2. Because this will also cancel out, and then you'll be left with eventually 286 divided by 143 will give you 2. Then equally this k's will cancel out, 0.25 to the x will also cancel out. So you'll be left with 0.50 to the power y divided by 0.25 to the power y. So you have to apply indices here. You apply indices here. 0.50 will give you 50 over 100. That would be half. And then half is the same as 2 raised to the power negative 1. So on top here, it should be 2 raised to the power negative y. Then 0.25 will also be 2 raised to the power negative 2. So the down should be 2 raised to the power negative y. So the laws of indices, when you do it well, you get this here. Is anyone clear with this? How I arrive? Are you all clear with this one? This part? How I move from here to this side? Or you need further explanation? Are you okay? Are you okay with this?
No.
Okay. So let's try and then solve this together. Let me. I hope you can see the Word document on your screen. Can you all see the Word document there?
Yes.
Good. So we had experiment 2 divided by experiment 1. So that gives us so on top there we'll have 2.86. The minus times the minus 6 will cancel out. So I'm taking those ones out. So over 1.43. So this should be equal to, then we have second part of the equation here. 0.25 to the x we are going to cancel out. So I'll be left with 0.5. Yeah, hello.
Sir.
Yeah. The is too small. Right? Yeah, hello, I'm listening.
Please, the numbers are not legible.
Okay, let me increase the font here. Okay, I think it is too much. So this is 2, oh, sorry. So we have 2 point. Is it better now?
No.
Is it okay?
Yeah.
Yes.
Okay, good. So 2.86 times 10 to the minus 6 will go away. So the down should give us 1.43. Then this should be equal to with the k to the k times 0.25x, they are going to cancel out. So I'll be left with 0.50. This is the same as 0.5 all to the power y. Good. So 0.50 is the same as 0.5 to the power y. Then this would be 0.25. Also to the power y. So I hope you are following so far. So when you simplify, this is what we will get. Now, when we use indices for this,
Sir.
yeah.
So is it 0.5 or 0.50?
Okay, you can still use the 0.50. You get the same result though. Let's use the 0.50 as it is. So from here, when you put 2.86 divided by 1.43 on your calculator, you get 2, right?
Yeah.
Okay. So we have 2 being equal to. Then when you do this there, 0.50, when you change it to a fraction, you get half. Right? You get 1 over 2.
Yeah.
And
Yes.
1 over 2, when you write it in terms of indices, it will become 2 raised to the power negative 1. Do you know that? In core maths, core mathematics. This one will become 2 raised to the power negative 1. Right? This will give you half. Do you agree?
Yes.
So this one also times the y will give you to the power negative y. Do you agree with that? Are you okay with that?
Yeah.
Yes.
Good. So should I put the fractions? So it means this will become 2 to the power negative 1, 2 to the power negative y, 2 to the power negative y, all over. Then 0.252 will give you 1 over 4. And 1 over 4 is the same as 2 raised to the power negative 2y. Are you okay with that? because this the 0.25 alone will give you 2 raised to the power negative 2. So times the y will give you this. So by the law of indices, we have two ones that will be used again. Two being equal to, this is division. So in division we subtract the powers. So we'll have 2 raised to the power, get the power symbol. So since we are dividing, we subtract the powers. So that will give us negative y minus 2y. So it becomes plus 2y. Sorry. So that will leave us with 2 being equal to this as short. We now have our 2 raised to the power y. You get that? Are you okay with that?
Yes.
Yes, sir.
Y will now give us 1. Okay. Good. So let me go back. Hey, who is that? Okay. So that is why you have y to be equal to 1. So when you do a similar analysis for experiment 3 over experiment 2, you arrive at x being equal to 2. So when you substitute the various orders, you get your rate law like this. So x was 2 and y was 1. Is it clear? Is that clear? I hope it's
Sir,
clear for everyone. Yeah.
please, how is S equal to?
You see the way we did this one? Row of time. We have experiment 3 being this one here. So you will have the rates here 11.40 over 2.86 times 10 to the negative 6. Then you equate it to this raised to the power x times this raised to the power y. I want you to try this on your own so that you get x to 2. Can you do that for me?
Sir, wait.
Unless you copy the table. You've not yet copied the table. Okay.
Okay.
So I'll be giving you the slide today. So experiment 3 over experiment 2. Oh, sorry. Please, we should all try to solve. We are wrapping up. So
Sir,
Yeah,
so which one become the X and which one become the Y?
your X values are the first table.
Oh, okay.
This is your Y. So
Okay.
you have 0.50 to the power X times 0.50 to the power Y, all divided by 0.25 to the power X times 0.50 to the power Y. Then you equate it to this over this. Hope you are all solving.
Yes, sir.
Yes.
Good. You should be fast because this is not your question. Your question is underway. The next slide. This is my question. So this one is just calculator work and then today I'm not hearing Buzel and Stephanie. It's like today the girls are quiet. What is happening? Oh, they are underground.
They seem they're going for a competition.
Eh.
Mm.
It's good. This is a healthy competition. So this one you can just employ your calculator. Yes, it's because you see that the 0.0 to the y's will cancel out.
Sir,
Yeah.
please, I'm done. Oh,
Did you get to? Where is that?
Manasseh.
Okay. Good.
Yes, please, I had to.
Very good. Who else? Okay, so those who are done, your question is here. You have a full question to solve within the next 8 minutes. We will look at the reasoning method later. So this is your table. So let me see whether I'll get. Let's try this. Yeah. So you try this very, very fast. You have barely 6 minutes more. So you just get the rate equation. Just get the rate equation. We'll look at the remaining aspects of the question in the next lesson.
Sir.
Yeah.
Yeah. Please, from this question, the way we divided the experiment 2 over
By
experiment 1. Sir.
yeah.
I'm saying that with this question, we divided experiment 2 over
By
experiment 1 to find the y.
yes.
And I wanted to know if, like, using the same experiment 2 and experiment 1, you can still find y from this. X.
It depends on the question. See, when your question, with the one I gave you, if you want to find if you want to find that is the b, right? Your b is your y. Your b is carrying the y, right?
Yeah.
The b carries the
Yeah.
y. If you want to find your b, the y for the b, you rather have to divide experiments 1 by 3 or 3 by 1 so that the 0.01s will cancel.
Okay.
Concept. Because this one, I know that if I divide 2 by 1, then anyway will go away. This
Okay.
will cancel out. See? That is why I did.
Okay.
So I was expecting you guys to use that reasoning skill. But
Oh, okay.
Sir,
we have not. Yeah.
sir, can I please go back to the question, as in the slide containing the question?
Okay.
Please, don't you think there is a mistake in the value of the concentration of the B for experiment 3?
That is a 0.13.
Yeah,
Why do you think it is?
because dividing the 0.13 by the 0.01,
Okay.
you get 13, and dividing the 1.83 times 10 exponents minus 3 by the 6.10 times 10 exponents minus 4, you're going to get 3.
Okay. So yeah. So
So,
you're different.
so
Okay. Finding the exponent to be a problem. Okay. So you said this by this went away, and then wait. 1.3. So then let's change the value to, I get you now. Are you all experiencing the same problem?
Yes, please.
Okay. So let's change it to 0.03. Would that be
Sir, please come again. What did you say?
0.03?
yeah, so
Will it be okay?
yeah, it will be okay.
Okay.
0.03. Okay.
Edit this slide.
Yeah, so now I'm done.
Okay. So can you share?
Oh,
Are you sharing?
Question said it.
0.03 for
Ah,
yeah.
okay.
Sir.
Yeah.
Can we just
God.
discuss the answers? The answers we got.
No, 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 no.
Let's try that.
Pardon?
Let's try that.
Okay.
Yeah, so any answers so far? I think I'll really have to alterate this question. So, Seth,